Okay, like we do. As always, we'll start with the review of last class. What did we talk about? Right. Before that, we started talking about system of linear equations, right? If you have a bunch of unknowns, x1 to xm, so these are all real numbers, then we are talking about solving for these unknowns when they satisfy a set of equations like this. And there are n equations like this. And what was the compact way of writing this? This was a compact way of writing this. And what are these? What are the sizes of these? What is the size of x? Is it n cross 1? What is x? What are the elements of x? So these are your unknowns, right? This is from Rm. What about B? So there are n equations. X1 a n m xm equals Bn. And what is B? What are the elements of? So it's B1, B2, Bn. This is from Rn. So what size would A be? N cross n. And what is A? What are the elements of A? M 1 A 2 2 A 2 M A N 1 A N 2, sorry, A N M. Okay. And then we talked about, the ordering of these, right? What happens if I switch x2 and x3? What changes here? In x, if I switch x2 and x3, does B change? B does not change. So what will be different about A? Okay, how will they be changed? I'm switching x2 and x3. Right. Third column becomes the second column. Second column becomes the third column. What happens when I, yes, when I switch things here? The rows. Okay. All right. Fine. And then, right. So we come across linear equations like this in two types of problems: control problems and what are these in general? What what are we talking about when we are talking about control problems? Right. We're talking about a system whose dynamics is determined by this matrix A, and there are a bunch of inputs that produce an output. There is a specific output that we want, and we are interested in solving for the input that will give me that output. Okay. About the estimation problem. Right. There is some system that we are interested in. It has a bunch of unknown parameters that we cannot directly measure. What we can measure is this B vector, and the relationship between x and B is, there is a linear relationship between them. So from these measurements, we are interested in finding out, okay, the unknown parameters. Okay. And then, okay, what did we specifically talk about? We talked about two interpretations of these, right? What is the first interpretation, or the one that we know from our high school? Review. Okay, and then let's take the same example that we did last time. Maybe another example. what would be the row view for this? How did we think of these equations when we were solving these in high school? What is the geometry associated with this? The first equation was a straight line. What would it be here? I think it'll be like this. Okay. What about this? So this is x1 plus x2 equals 1. Here it's if x2 is 0, it's 3. So this will be something like this. Okay. This will be x1 minus x2 equals 3. And when we say we are interested in finding a solution, and we can find a solution here, what are we really talking about? Geometrically, we're talking about this point. If you solve this, what do you get for x1 and x2? What is x1? It's b2, no? And minus 1? Yeah, it looks like that. 2 minus 1, 2. Okay. The intersection of those 2 points is this point. Intersection of these 2 lines is this point. 2 comma minus 1. And that's what you get. Okay. This is what we are used to. What is the other view that we discussed yesterday? So now we can write this as what? In the Ax equals b form. What will the elements be? Okay. Okay. What is a column system? Huh? Right. Instead of viewing the, associating a geometric structure with each equation, we take the individual columns. The individual columns come from R2. Okay. This is R2. We ask, where is the first column? First column is here. This is A1. That's this. Where is A2? A2 is 1 minus 1. That's here. This is A2, A1. And what is B? 1, 3. So this is 1. This is 1, 2, 3. Here. Right? Okay. When you write Ax equals B, what are we really doing? What are we really saying? If you expand this out, remembering what happens when you post multiply a matrix by a vector, this would come out to be x1 times a1 plus x2 times a2 equals b. So what we're really asking is how much do I scale a1 by and how much do I scale a2 by? And after scaling them, if I add them together, I should get b. So we're essentially asking how much do I change this length or change a2, and then if I add those scaled versions, I get b. Right? The solution is you take 2 times a1 and you take minus 1 times a2, and that will give you, right? That means 2 times a1, that's here. That is 2a1 minus 1 a1, that's here. And the sum of these two is this. This is 2 times a1 and this is minus a2. Okay, that's the column view. Okay, right. See, now you could ask, okay, okay, before we go, right? This is where we stopped yesterday. Now, starting with the column row view, in the R2 case, in the 2 by 2 case, when would you have when would you have a unique solution for Ax equals b, where A is from 2 cross 2. Using just the geometric picture. When would you have a unique solution? Only one solution. Sorry? No, don't go to the don't go to the span. Remember from your again uh, from your high school mathematics, in the standard view where each equation represents a line. What is the geometric condition on the lines for you to have a unique solution? When exactly when do they intersect at a point? At one point. Is the question clear? If you're talking about two lines in R2, when will those 2 points intersect only at one point? In line, we are only talking about straight lines. No, yes, but that's not. I just that was the question. I mean, when they're not parallel to each other, right? As long as they're not parallel to each other, they will always cross, right? So in the row view, not parallel implies unique, implies a unique solution. Okay? Is it possible for you to have no solution? This is an example of, uh, right? So if I have R2, if one equation is like this and the other equation is like this, these two will never meet. That means this has no solution. This is, for example, in the previous case, let's say the first one is x1 plus x2 equals 1, x1 plus x2 equals 4 has no solution because you cannot have values of x1 and x2 that which will both which will add to 1 and give you 4. It will only give you one of those. So there is no solution here. Is it possible to have any other? Are there any other possibilities? Can you have two solutions? We know that there are infinitely many solutions. When would that happen? Yeah, it's the same line. So if I had written 2 times x1 plus 2 times x2 equals 2, both are the same equation. That means we're talking about the same line on top of each other. That means any number of x1 and x2 or infinite number of x1 x2 will solve this. Okay. So when you're dealing with linear equations, so same line. When you're dealing with linear equations, these are the only three possibilities. Okay. If they're non-linear, of course, you can have anywhere in between 1, 2, 3, 4. But if it's linear, these are the only three possibilities. Okay. Right. This is for R2. Okay. This seems simple enough, right? What R3? It's right. R3 will look like this. Let's say x1 plus x2 plus 3 equals 1, 2x1 plus 3x2 plus 3 minus 5, x1 minus x2 minus 3 equals 2. Now, if you're talking about three equations and three unknowns, what do each of these equations represent now? This is an equation for a plane. Okay. So we're really talking about now planes in R3, two-dimensional planes in R3. And when we say we want to find a solution, we're saying uh, we are looking for the point that corresponds to three planes in R3 that intersect, and they intersect, and depending on again the nature of these planes, we are asking what are three different possibilities. Okay. In R3, when would you have a unique solution? Right. The three planes cannot be parallel to each other, right? Okay. It seems like a reasonable answer, right? Based on R2. It turns out that is not enough. Okay. So let's talk about this, right? When will you not have, well, infinite number of solutions is easy. If all three planes are the same plane, then infinitely many solutions. When will you not have a solution? Right? There are multiple possibilities, right? Uh, Here, you can have three planes that are all parallel to each other. You can have two planes that are parallel to each other, or let me say, okay, imagine the line is the plane and it's coming out of the board, right? These are all three planes. If you have a situation like this, no solution. If you have a situation like this, two are parallel to each other, the third one is not parallel to either one of them. Here also you don't have a common solution, right? Or you have a situation like this. Right? It gets a lot more complicated when you go from R2 to R3 if you still stick to this row view. Okay, it turns out the column view is much nicer because it's the same interpretation. Okay? So you can see the problem in R3 if you stick to this row view. So this is a restricted view. In an R2, it works very well. Beyond R2, it's not easy to work with this. But if you look at the column view, what are we talking about with this? Column view, we're talking about A. Yes, we're really saying there is one A1 here, some A2 here. Imagine now these are in three dimensions. This is what I've drawn here is R3. And then there is some B here. Okay. In the column view, all we are asking is, so we have our matrix that is 1, 1, 1, 2, 3, 1, 1 minus 1 minus 1. This is the first column, second column, third column, and that gives you some B. All you're asking here is how much do I uh, stretch these three vectors? And if I add them together, I need to get this vector B. Okay. Now, let's go back to the R2 case again, right? Here. And then talk about these three situations, but from the point of view of the column view. Okay. Let's do R2 first. Okay. So we'll stick to the column view. We'll never come back to this view again. We'll always only talk about the column view. So we'll look at some examples and then try and understand the different possible cases that you could have and how they are related to the columns of A. The same example that we had yesterday. Two. Was it one? Okay. What are the columns? A1 is 1, 1, 2, 1. This is A1. And B is some 1, 3, B is here. So in this case, when would you have in this case, do we have a unique solution? In this case, there is a unique solution. That means for this particular case, I have a unique solution. But what if I put some other B here? Not 1, 3, but some other B from R2. Will I still have a unique solution? Yes. So now, if I choose A1 and A2 are not collinear, what can you say about the span of A1 and A2? Well, span of A2 is this subspace. Span of A1 is this subspace. But the span of A1, A2, the set A1 and A2 is R2. It spans all of R2. So any B that you give me, I can solve for B. Okay. But there are multiple possibilities, right? You can either solve it with a unique solution or infinitely many solutions, right? It turns out in this case, whenever B lies in the span of A1 to AM, whenever you have this situation, then you do have a solution. Okay. and if this set is linearly independent, okay, then it turns out you have a unique solution. Okay. Maybe this is not immediately clear, but I hope at least this is clear. As long as if B belongs to the span of the columns of A, then there is always a solution. Okay, because when you do AX, right, you're simply taking the linear combination of columns of A. Okay. Now, what if instead of an A like that, if you had an A that was this one is 1, 1, 2, 1, or instead of just having 3 A's, now you have a situation where you're dealing with 3 columns of A. And instead of having 2 A's, you have 3A. Sorry. Instead of having 2 columns in A, you have 3 columns in A. The corresponding picture. So this is A1, A2, -1, -2. Here. This A3. Okay. Now, what is the span of? This is still R2, right? That means no matter what B you choose from R2, I can always scale these vectors, add them together to get to that B. Okay. But will it be a unique solution? Is there only one linear combination of A1, A2, A3 that will give me any B? For example, let's say this B. What did you guess? Why? Right. See here. This is R2. What is the dimension of R2? 2. Why is it 2? Yes. Because if we take a basis for R2, the number of vectors it can have is 2. That means with just those 2 vectors, I can get any vector in R2 by taking a linear combination. Okay. And when you say a basis, the basis is a set of vectors that is sufficient and necessary. You cannot add, if you add anything more, you can still get R2, but there are infinite number of combinations that will give you R2. But if you take one out, you don't span R2 anymore. Okay. So a basis is sufficient and necessary. Okay. So if you have 2 vectors here, you can uniquely get any uh, vector from R2. What's changed here? The span still remains R2, right? But what's changed is now we have an additional column. That column is redundant because we could have gotten this B by just combining A1 and A2. Okay, let's forget about A3, right? Let's say there is a combination that produces B, right? Instead of producing B, I could have produced 2 times B, and then I could have used A2 and A3. These are still linearly, A2 and A3 alone form a linearly independent set. I could have formed minus B, and if I add them all together, I still get B. And now you can imagine any number of other combinations that you could have produced. So what you have here is then infinitely many solutions. That's because your columns now, even though they span R2, they are not a basis for R2. Why is it not a basis for R2? Not in this case. Why is it not a basis for R2? No, it's not. It's not linearly independent. A basis has to be linearly independent. It has to span the space. It spans the space, but it's not linearly independent because I could have produced A3 from the linear combination of A1 and A2. That means if alpha 1 A1 and alpha 2 A2 give me A3, right? Then if I simply choose alpha 1 A1 plus alpha 2 A2 minus A3, this will produce 0, where the alphas are not 0. That means this is not a linearly independent set. Yeah. So this is not a basis for R2, even though it spans R2 because it's not linearly independent. Whereas there, no matter what linear combination of A2 you take, you can never get A1 because all you'll produce from A2 is just vectors from this line. Similarly, from A1, all you'll produce are vectors from this line. That means they are linearly independent. And they span R2. That means the columns of this matrix do form a basis for R2. So whenever the columns of your matrix form the basis for Rn, okay? Okay, let's make general statement now. If you have A is a n cross m matrix. Okay. Whenever the columns of A form a basis for Rn, then you have unique solution. Just remember this for now. We'll come back to this a little later. Okay. Now we've seen a case where we have a unique solution. We've seen a case where there are infinitely many solutions. Now we'll look at a case where A is simply this. What is the corresponding set of linear equations here? I've given you A and B. How many unknowns does this have? Does this problem have? What is the size of X? 1. Right. So what are the equations then? There is only one unknown. Let's say that's X1. So X equals X1. How many equations does it have? 2. What are the equations? 2. Okay. What is the column view? A is here. Okay, where is B? This is A. This is A1. This is B. Is there a solution? Are there infinite solutions? Why is there an okay? All right, tell me all the don't tell me the all infinite solutions. Tell me at least 2 solutions if there are infinite solutions. Right. So there is only one solution, right? See, B is 2 times A. That's it. That's the only thing that will produce. You have to stretch A by A1 by 2 times and you get B. Okay. From the geometric picture, when will I not have a solution? Let's say I don't have a B. We want to come up with a B such that there is no solution. Right. Any vector that does not fall on this line cannot be obtained because we are talking about Ax equals B. That means the only thing you're allowed to do to this vector is scale it along this line. That means the moment you have a vector that is not in the span of the columns of A, then you have no solution. Right? So give me an example. A numerical example of B that is not solvable. Okay. Yes, phi 3 is not solvable. The two equations that we have is x1 equals 5, x1 equals 3. That's not consistent. So this has no solution. Right? So whenever you have a situation where V does not belong, okay, to span of columns of A, then you have no solutions. Okay. Okay. Now let's look at a situation like this. Okay. There is some B, or let's put it like this. If you see A like this, what all possible solutions can this system have? We don't know B. B can be anything. Okay. Can you have a unique solution? Why not? They're linearly dependent. Okay. All right. Fine. I don't know why that will produce. I mean, I'm not sure why that will produce infinitely many solutions, but I'll take it. I'll take your answer. Can you have no solution? This in this particular case. If you're not sure, just because it's R2, just draw the picture and then you tell me. What is the picture? So this is A1. This is A2. Yeah. So you can have no solution. Yes. When you have no solution, when it's out, when it's here or here, it doesn't matter. The moment it moves a little bit outside this line, you have no solution. But what happens when it lies on this line? Then you have an infinite number of solutions. Why? That the linear dependence thing that you said. It's the same as here. I mean, here the span of the columns of A was from R2. So no matter what B you chose, you could always solve it. Okay. And because you have more than what you need, because this is not a basis, that's why you had infinitely many solutions. Whereas here, you either have no solution or infinitely. Here you always have infinitely many solutions. Whereas here, you, well, here in this case, you either have a unique solution or no solution. Whereas here you have what? What are the two possibilities? No solution or infinitely many solutions. Okay, is it clear? So it looks like what really matters in determining whether you have no solution, infinitely many solutions, or a unique solution depends on two things, right? What are the two things? Right. It depends on what is the span of my columns. What is it in normal words? When I say span of the columns, what am I really talking about? Or no, no, linear combination of the columns. That means what all can I produce by simply stretching my vectors and adding them together. Okay, so it depends on the span and whether or not the columns form a linearly independent set. Okay, if you know these two, then you can figure out which of the three possibilities you have. Okay, all right. So we'll now kind of bring it all together and maybe have a simple set of rules to help us identify which of the three cases we have for a particular system of equations. Right. Let's start with the first case. Let's assume our A is full rank. What does it mean? Right. So if we say full rank, so we will always assume that this is n cross n. uh, rank of A is minimum of n%. Okay. Now, if it's full rank, right? Here again, it's not that simple. So because you can have multiple cases like this. Okay, all three are possible: square, fat, or tall. Okay, let's start with this. What happens here? If A is square, A is full rank, and it's square, then what do we have? Right. That means, I mean, both are equal. That means you have a linearly independent set of columns or a linearly independent set of rows. Okay. And what is the span of the columns of A? Rn, because n is equal to m. So this is nn. The span of AI is Rn. Where is B from? Rn. Okay. Uh, and do the set AI, does this form a basis for the span of for its span? It does, right? Because this is a linearly independent set, it spans. So that means it must be a basis for its span. It turns out its span is Rn. So this is linearly independent. That means the columns form a basis for Rn. The moment you have a basis, you can solve for any B and you can solve for it uniquely. That means you always have a unique solution. Okay? When you have full rank and it's a square matrix. Okay? Right. What about this? This is N. This is M. What does it mean? If you say, what is the rank? Okay. R is N. What is the span of the columns of A? Why is it Rn? Rm, is it? Somebody said the span of the columns of A is Rn. Why is it Rn? Yeah, there are n linearly independent sorry. Yeah, rank is n. That means there are n linearly independent columns. That means I can get any vector in Rn. So this is Rn. B is always, I mean, B is from Rn. That's okay. So, and then next, what about AI? Is it a linearly independent set? Do the columns form a linearly independent set? How many columns do we have? M. M is greater than n. That means there are more than n columns. So that there are more columns than you need then to reach the span. So this is linearly dependent. So what? So what will be the there are infinitely many solutions. Sorry. Okay, many. Is the argument clear? Okay. What about here? N, M. What is the rank? M. Okay. What is the span of? What is it? R M. Hey, hold on. If I have matrix like this, here R, here M is 2, right? It's R2. These vectors are from R3. There is no relationship between R2 and R3. So the span is not R2. It's not Rn. But you are correct in one way. The span will always be in Rn because you're taking the linear combination of vectors from Rn, right? This will be a subset of or subspace of Rn. No? Okay. Here, in this case, this is the tall case, right? The vectors from R2, the columns are from R2. What is the span of the columns of A here? It's this line, right? This one. And this is a subspace in R2, right? That's what I've written there. The span of the columns of A will be in R2, but it won't be Rn. Why? It'll be smaller than Rn. Because M is less than N, that means there aren't enough columns here for me to reach all of Rn. That means what I can reach has to be smaller than Rn. That's what this means. Okay, so you can only get a subspace of Rn by taking the linear combinations of the columns of A. That's what we've seen here. This is from R2, but there is only one vector. The linear combination of this will simply produce a one-dimensional subspace in R2. You were right you were not right. You said Rm. Maybe what you really meant was what you will generate is a m-dimensional subspace in Rn. Okay, because there are m vectors here, they form a linearly independent set. They span their span. Whatever is the span of this, it's able to produce all that. That means the columns that you have here form a basis for its span. Okay. If you have a set of vectors, okay, x1 to xp, you take the span, it produces some subspace. Okay. If this set is a linearly independent set, okay, I am claiming that this set is a basis for the span of its span. This is the basis of its span. Is it clear or no? Here, what is the span? It's this one-dimensional subspace, this line through the origin. I ask you, does A1 form a basis for this subspace? When will a set be a basis for a subspace? It has to be linearly independent and it should span that subspace. Okay? The columns of A will always span the span of columns of A. Okay? And if it's linearly independent, that means it forms a basis for the span of the columns of A. Okay? And what is the dimension of a subspace? How do you determine the dimension of a subspace? No, it's not the span. Number of vectors in? Yes. No, no, no. It is the number of vectors or number of basis vectors in its basis of any basis, right? Here. The m columns here form a linearly independent set. Okay. That means they form a basis for its span. Okay. And what will be the dimension of the span of the columns of A? M, because there are m vectors here, and these form a basis for the span of the columns of A. That means that what you get here is an m-dimensional subspace in Rn. Okay? So come back to this example. You're dealing with R2, but because you only have one column, all you can produce is a one-dimensional subspace in R2. Okay. Now imagine if you had a situation like this, or here, 1 0 0 0 1 0. Say you had an A like this. What is the subspace that you can produce with this? Imagine the first element is the x-axis, y-axis, and the z-axis. Right? With these two vectors, what I can produce is the xy plane. Because here, z is always 0. I can get any x value and y value by, if I want the x value to be alpha, I multiply the first vector by alpha. I multiply the second vector by beta. If I add these two, I get alpha, beta, 0. Means I can produce any vector of this form. This is nothing but the xy plane. Okay. And what is the dimension of that plane? It's 2. It's a two-dimensional plane in R3. Now, instead of this, if I had A11, A12, A21, A22, A2, A31, A32, and let's say these two form the linearly independent set, the columns of A. That means they form a basis for their span. That means the dimension of their span should be 2, because there are uh, two columns. Okay, all right. I'll stop there. You can think about that later. Okay, all right. Yeah, okay. Do the A's form a linearly independent set? They do, right? The rank is M. That means there are M columns that you can choose from the columns of A that will form a linearly independent set. That means that there are only M columns. That means they have to be they have to be linearly independent. This is linearly independent. Yes. So what can we say about the solutions of this type of a system? Will it always have a unique solution? Right. There is one condition. When you have systems like this, there are two possibilities. Okay. Especially when you're dealing with full rank. If B belongs to span of the columns of A, no. Then you have a unique solution, right? Because B is from the span, these form a basis for the span. If you have a basis, that means you can always find one way of reaching any vector in that span. So that means in this case, you will have a unique solution. What about when B does not belong to span? That's this case, where it's outside my span. That means I cannot reach that vector. Means I can never reach B. That means here you have, I'm running out of space, but no solution. Is that clear? Okay. That's only the rank, full rank case. We still have to look at what happens when A is rank deficient. Is it clear? Okay. Now, when A is rank deficient, okay, that means R is less than minimum of n comma m. Again, we'll talk about these three cases. Okay. See, one thing is always clear when you have a rank deficient matrix. What is it? There is never a unique solution. So this is a little easier. If it's rank deficient, then you know no unique solution is possible. The only possibilities are either no solution or infinitely many solutions. Okay, let's look at this here. What possibilities do you have? N. The columns don't form a linearly independent set. Okay, that means unique solution is gone. What is the span of the columns of A? Is it Rn? Let's say the rank is R. Is it all of Rn? Can you span all of Rn if the rank is less than N? You can't. So this will be a subspace of, right? What will be the dimension of the subspace? Yeah, what? It'll be the rank, no? R. Because the rank is the number of linearly independent vector columns that you can take from this matrix. If there are only R uh, vectors here that are linearly independent, that means if I generate their span, they will only produce a R-dimensional subspace. Okay, so the dimension of this is R, not linearly dependent, or let's say linearly dependent. So what can we say about the solutions? No unique solution. When will you have do you always have infinitely many solutions? Again, B belongs to span AI, then infinitely many solutions. And if it does not, then this is probably, in fact, I will not do this. You have the same situation here. Okay, the same thing applies. Whenever you have rank deficient system, there is no unique solution. If B belongs to the span of the columns of A in each of these cases, then you have infinitely many solutions. If B does not belong to the span of the columns of A, then you have no solution. Okay. I mean, it turns out this is also too much. You can actually compress this even further. You can, so all you have to do is if rank of A is less than minimum of, no, yeah, no, just two things. You only have to remember two things. See, it's important that you're able to argue through all of them, this detailed argument, but it's useful to remember this. If B does not belong span of AI, the columns of A, then what? B is not in the span of the columns of A. Then you cannot get it. So this is always no solution. Now let's say B is, sorry, span of. Then there are two cases. What are the two cases? Right. What is the right? What is the linear dependence relationship in terms of the rank? Don't tell me. Let's talk about it in terms of the rank. What is the condition on the rank of the matrix R for the other two cases? For unique and for infinite linear. Yes. Hold on. Is that right? Yeah, good point. You said, okay, rank should be equal to the minimum of n or m. Is that right? You are right. Hold on. Okay, let me think. So this is equal to m. No. See, when will B always belong to the columns of span of the columns of A? Let me think. When it is m, so when it's minimum, then it's okay. When it's minimum here, yeah, that's fine. Yes, you're right. Yeah, then minimum n cross m. If it's less, then there are infinitely many solutions. Because before you check this, you've ensured that this B is there. So it's fine. Okay, so this is essentially the condition. Yes, that's the rank argument. No, rank tells you how many linearly independent columns you can take from A. So I replaced the linear independence argument by rank here. Okay, all right. Okay, now, so these are the different possible cases, and this is the condition on A and B for the system of linear equations to have these three different possibilities. So now if you have A in n cross n, in the most general case, let's say we do have a solution. Okay, we're not worried about no solution case now. See, we have a situation where we can solve it, right? You can either have unique or infinitely many solutions. It turns out if you have X equals B, right, the most general form of the solution is something like this. X is usually written as xp plus xh, where x is a solution. Okay? xp is called a particular solution, and xh is called the homogeneous solution. Maybe you already know what those are. What is a homogeneous solution? Right. So all we're saying here is if you have general set of equations like this, which we know has a solution, then you can always write the solution in this form as a sum of a particular solution and a homogeneous solution. And if you take xh, we're claiming this will always produce B. That's because xh, the homogeneous solution, is simply the set of x, okay, such that a times x is, okay, set of all possible x's, such that if I do a times x, I always get 0. If that is the case, if that is the definition of xh, then if I expand this out, xp plus a xh is b. This is equal to 0 because by definition it's 0. Okay. This xp is simply a solution that solves ax equals b. Okay. You can choose anything. Anything that produces b, that is a particular solution. And if to that particular solution you add any homogeneous solution, there are any homogeneous solution, then xp plus xh will still produce p. I mean, this is also a possible solution for your problem. Okay. Okay. Let me ask you a strange question now. Where is xh from, or where are these elements from? X. What space? Rn or Rm? Rm. Why is it from Rm? A is n cross m. It maps from Rm to Rn. I'm simply saying x are all the vectors which A maps to Rn. That means these have to be from Rm. Okay. All right. Okay. Now you have that set, the set of homogeneous solutions. Now the question is, does that set form a subspace of Rm? I'll call it capital XH. This is simply the set of vectors belonging to Rm, such that A times x produces 0 vector. My question is XH okay, the subspace of Rm? How will you verify? Yeah. If yes, you have to give me the reason. If no, then again you'll have to reason. What are the conditions for a set to be a subspace of something? Is it a subset of Rm? It's a subset because the elements are from Rm. Okay. What are the conditions? Okay, subset, one condition is satisfied, there is another condition. It has to be what? It has to be a vector space. What are the conditions for you to verify if it's a vector? Yeah, can you verify? How will you verify? Right? Yeah, okay. Let's say we take a vector y from xh. Okay, so okay, so if this is from ah, right, that means a times y has to be 0 because that's by definition. If you say this belongs to xh, this is the condition that vector needs to satisfy for it to belong to xh. Okay, okay. So what? So if you want to test this scaling condition, you take y, you multiply y by some number alpha. If you now multiply this by a, do you still get 0? Yeah, you get 0. The scalar goes out. So this is a times y. A times y is 0. So this is 0. So it's closed under scalar multiplication. Okay, what about vector addition? There you have to take two vectors. Let's say we take z. Okay, I know a z produces 0. If I simply add these two, that's simply a y plus z equals 0. Well, addition of two vectors from the homogeneous set. So this is in fact a subspace of. Okay. All right. See, now we will take a closer look at um, the nature of the solutions that we get when we solve for x equals b. Say we take a 2 by 2. Okay. Okay. What is the column view? A1. This is A2. The vector that I'm looking for, 2, 3, is 2. That's here. This is B. This is A1. This is A2. Okay. And this is Rn, which is equal to R2 in this case. Yeah. What is the solution for this? If you solve for this, what do you get? Can you tell me? What is the solution? What what do you get? Okay, some weird number. No, let's simplify this. It's fine. No, don't worry. Let's do this so that the numbers come out a little simpler. Maybe that's also too complicated. Sorry. Do this. I'm sorry. Yes. Yeah. Okay. 1, 1. Okay. See, we know this matrix A, right? What does it represent? What do matrices represent in general? Any n cross m matrix. It's what? Right. Well, matrix is an array of numbers. What does it represent? Linear transformation, right? Matrices represent linear maps from Rm to Rn. This is a 2 cross 2 matrix. That means it represents a map from Rm, which is R2, to R2. Okay, right? So you have this vector B. Okay, you obtain this vector B from a vector X. Okay, and the way you obtain it, you take X, you multiply by A, and then you get B. Okay, now this vector X comes from Rm, and what you produce by doing Ax comes from Rn. Okay. In this particular case, that B is produced by this vector X, right? Okay. There is a difference between these two R2s. This is the output space of A. This is the input space of A. Okay. This vector from the input space gets mapped to this vector in the output space. Okay. And because this is 2 cross 2, full rank, there is a unique solution. A single vector from here gets mapped to a single vector here. Now, if you choose some other B, well, this is not the B we are talking about. This is the B we are talking. Sorry, this gets mapped to this. If you choose some other B like you did here, you'll have another vector that gets mapped. So every vector here has a unique, uh, or every vector here gets mapped to one vector there, or every vector here has a unique vector here that will get mapped to whatever you have there. Okay, right. That's when you have the full rank case and square matrix. Okay. Now, let's do another example where you have what is input space, what is output space, what is Rn, what is Rm, what is Rn? It's R2. So yeah, this is R. What about Rm? It's R1. It's simply the real line. It's just simply R1. Okay. And our vector, the column is 1, 1. Where is our B? B is 2, 2. This is A1, B. That's the span of the columns of A. What is the solution? It's 2. Okay. Means 2. This is X. This vector from R1 gets mapped to this B. Okay. If you choose another vector, let's say -1, what will that get mapped to? It'll get mapped to minus A1. It'll get mapped to -1, -1. Okay. So points on this line from R1 get mapped to this one-dimensional subspace in R2. Okay. What about matrix like this? What about a situation like this? What is R2? What is the size of R2? Sorry, Rn. It's R. Input space Rm is R2 now. Yeah, we'll come to that. Yeah. What is the solution for this? How do you solve this now? What is the nature of the solution? Unique or infinitely? We're not dealing with no solution. Okay. Can you write down the solutions? In the general form, you can write it as a particular solution plus what? Homogeneous solution. Can you give me an expression for that? So can you tell me what it will look like? What will the homogeneous solutions look like? Homogeneous solutions are when you take 1, 1, the matrix, and then you multiply it by xh, you get 0, right? Xh, if this is nothing but x1, x2, that means x1 plus x2 is 0. That means x1 equals minus x2 is the homogeneous solution. It means any vector that you choose for x. So xh will have vectors like of this form. Well, I'll write it as x2 equals minus x1. So if the first value is alpha, that's x1. x2 is minus x1, where alpha is any real number. Okay, if you choose any vector like this and you multiply it by a, you will always get 0. Okay, so that's my homogeneous solution. If I want to produce 2, if I choose x to be 1, 1, it will produce 2, right? So that means if my solution, that my complete solution is x equals 1, 1 plus alpha minus alpha. Alpha is any real number. If you take this and multiply it by this matrix, you will always get 2. That means all points of all these points, whatever points you can generate with this equation, will all get mapped to 2. This is what we want. So here, okay, that's 2. That's your B. Where are the columns here? I mean, we were drawing the column vectors there, right? Where are the column vectors here? In this particular case, what are the column vectors here in this case? It's 1. There are 2 column vectors. Both are a1 equals 1, a2 equals 1. That's it. Okay? Because you have more than what you need. This is a one-dimensional space. You only need one vector to form a basis, but you have two linearly independent. That means you have infinitely many solutions. Right? Now, we saw earlier that the homogeneous solution forms a subspace of Rm, right? What will the subspace Xh look like here in Rm? Well, it's any set of all points that look that where the first coordinate is alpha, second coordinate is minus alpha. So it's alpha, it's minus alpha. So it will be this. This is Xh. Okay. But look at the solutions. The solutions for this problem are the homogeneous solution plus some vector 1, 1. That means I take this line, or put another way, if I take any point on this line and I add the vector 1, 1, that 1, 1 vector is this. This is this vector 1, 1. If I take any point on this subspace and I add this vector 1, the resulting point that will get mapped to B. If I take another point here, I add 1, 1, that'll give me a point here, that'll get mapped there. So it turns out, now the set of all those points is simply this. A line that does not pass through the origin, that means it's not a subspace, that is parallel to the homogeneous solution, and it's shifted by some amount. Okay, this shift that you have is given by is your xp. Okay, now like you said before, an entire line from R2 from the input space gets mapped to this output space, the real line. Okay, maybe you're seeing a trend here, right? In the first case where it's square and full rank, entire R2 gets mapped to entire R2. A two-dimensional space gets mapped to a two-dimensional space. Here we are talking about one-dimensional input space, two-dimensional output space. But what really gets mapped is this one-dimensional space gets mapped to a one-dimensional subspace in R2, even though you're dealing with a bigger space, right? Whereas here, the output space is one-dimensional, right? Even though the input space is two-dimensional, entire lines get mapped to one single point. Okay. All right. So with that, we'll stop now, and then we'll take this again. We'll continue this next Thursday. Okay? Are there any questions before we conclude? Yes. Yeah. Yes. 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 Let me think. Okay. Then I've done a mistake there. Okay. Her point is, if you have B belonging to the span of columns of A, and then I said if the rank R equals minimum of n comma m, then I said it's unique, right? And if it's less than, then I said then it's infinitely many solutions. That is not satisfied here. B is in the span of this. The rank is the minimum of these two, but you have infinitely many solutions. Okay, then I've messed up somewhere. What would it be? It would have to be not this. Okay. The rank would have to be m, the number of columns. Okay. If B belongs to the span of AI and the rank equals the column rank, that means the number of columns, then you have a unique solution. Okay. The argument would be B is in the span of the columns of A. Okay. That means I can reach B by taking the linear combination of columns of A. Okay. If the columns form a linearly independent set, then there is a unique way in which I can reach B using the columns of A. The columns of A will form a linearly independent set only if the rank is the number of columns. Okay, so the condition would be this. So you can correct that. I think it's in the slides. It's okay. In the lecture, I messed up. This is the condition. Yeah. Thank you, Manish. Yeah. Yeah. You simply have to replace minimum of n comma m by m. If B is in the span of A, the rank should be equal to the column rank for you to have a unique solution. Rank should be equal to the number of columns. Okay. All right. If there's nothing else, we'll stop here. See you guys Thursday.